So yeah, I was doing this. Right? So, yeah, this one. This is where I left off. Okay, so yeah, so what we have to basically do is just get the error over here that we figured out by doing all this shit later on, and then changing this percentage back into this, which you can do with looking at the chart and doing the same thing they're doing, basically copy and pasting, plug into a calculator the plus and minus this, and you realize that 50 is the only one that's weird, but everything is fine, so we can actually safely say kind of that n equals 150. But if you really want to know what reflection is, just for fun, because I actually need to do take a class, I'm about to take a test on it for another physics class. It's basically light going in and it's reflecting at the angle. So if I do something like, oh, so actually that's a bad example because perpendicular light will always go straight. So if you go to angle like this, it's basically the angle over here. How much reflection is there? It's always a straight line although. So this is a freaking horrible picture. So if a line goes over here, it's basically saying, oh yeah, it goes reflection over here and the angle over here and then go over there is different. And imagine if this is like some kind of medium. I don't know. Medium can be water, it can be something else. There's also another thing where the light actually can bounce off, which is a different type of light. But if it's water, it's not significant because most of the light goes through, and not a lot of light goes this. But if it's not water and something that you kind of know, a mirror, it just goes like this. Very interesting topic. I'm pretty sure it's not part of this class, anyways. It's part of this class. I'm gonna have to explain physics 2C. Anyway, next portion is getting the idea of this down. So this is very confusing, and the reason it's confusing is because what is this compared to this? Yeah, so this. So if I get the what was asking for a measure that needs a final sensitivity of 0.03. Oh, okay, yeah. So um, this is SD, and SD equals 10 meters per second. Um, Standard deviation is given by 1 over n minus 1 by the total amount of the average minus everything else. And then you get that n u, and once you get the average, you need a plus or minus about the average, which means you need to do this divided by square root of n to get the average uncertainty thing. And that's what we have over here because truly random average. Over here's average there, right? Many to give a final uncertainty of 0.3. So we just have to do this over here because the claim is that every all standard deviation is this. So if I look at what chapter is this, chapter 4. Um, if you look at chapter 4, there's something here. Since about so here where is it? So the average uncertainty of individual measurement x1, x2, x2, xn is given by a standard deviation or SD. The definition SD is called sample standard deviation. Is the most appropriate for our purpose. The population standard deviation is called blah 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 blah, and then that is standard deviation. And then the standard deviation of a mean is then over here in the textbook it shows equation over here, which is important to show that the mean standard deviation is this, and then the error deviation is, and yeah, which, yes, it's fine. Yeah. So we can go to the next section. I think, I hope I can, because I don't think there's anything more to talk about there. Oh, yeah, no, there's something else. Part B. How does the advantage of the only zero? Oh, the same thing over here as we do over here. And we get 400 amount, which is incredibly large, which I don't like. but it makes sense because this is 1 over half, and just flip it over because we have the division over here, which is 20 divided by 1, which is square root over here, which equals 400. Over here, we round down. I accidentally round up first, which is why I crossed it out. I could have erased it, but I was lazy. And over here, so it's just basic algebra, moving this over here to get n, because n is the number of things we have. And so if standard deviation is always the same, the only thing we can change is the number of count, which is why we have this. So it's not saying that the standard deviation is not changing. It's definitely is changing. It's just that because it's a fact here, is confirmed, is given, you can't really change it. If you're giving more precise measurements later on, it wouldn't. You can't say anything about it, so you have to move on from it. So the only thing you can change is the numbers for now, and which is why this equation is there, because that's the only equation you can use for that 4.18. Yeah. So I first wrote this because I thought it wasn't given, but it was given over here, which is my stupidity over there. So you do this and you boringly put this over here. So the answer actually rounded up to 40, which I didn't know. So great. You might. That's why I said the answers might be a little different here when we over here might be a little different over here because by rounding here, which yeah, I didn't. I didn't. Whatever. You do the same thing basically. What so A is not really anything too noteworthy. Really, it's just basic like doing the average and did I do the average over here? Where's the average? Average, you plug in these into a calculator and get the average over here, and then do minus 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 blah 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 with n minus one using the freaking this, and then you get the this over here. The noteworthy thing about A that's different from 4.18 is that we actually get the definition of the mean error for R, the uncertainty for R, which is the key point in A that I think the professor wants us to realize that for this question, standard deviation equals to the error of the mean, which is over here, and then we just get square root of 4 and blah blah blah, everything else is the same, and you just get this, and I said, yeah. And over here, part B, we have a system error. At first, I didn't know what the fuck they were doing, but as I looked at the textbook and noticed that this is a percentage and this is a percentage, and we know about how percentage error comes into play when dividing and multiplying. Whew. And because of that, we can use this, and then we use the same strategy because R equals I divided by V, if I'm not correct. The V divided by R, which is division, which you can use percentages on. Clever, right? And that percentage error shenanigans we have, percentage first of all, it's actually written in the textbook, but I didn't connect the dots until I did all the homework again. So to get it faster for you, faster if anyone else is listening to this thing, which I don't really care if you don't. So over here we have percentage, and we get percentage over here to square root, which gives you this over here, which is error versus R, which is a percent. So I can multiply this by 100, but I just leave it there because I could just multiply this by this over here to get something like here that's happening. So 0.7, and you plug it into these two because we have this equation over here, which is saying my head's just random, which is this over here, random check, plus system error, which is this over here, system error 0.7. We plug it to here to get 0.01, but since this is not 1, we can just leave it as 1 out of 7. So the final answer is, I think I left it here then, this. Makes sense, right? The key part, I think the professor wants to assign this question, because this is a assigned question like the other one. The non-assigned question, I don't really know the reasoning for for doing it. It's optional. Like this one has no purpose at all for being a question that the professor gave because it's optional. But this has a reason. This is a percentage, another use of percentage, which is something that I didn't even think about. That division can be used as a percentage thing, and then you can use that as a system error. Uh, and all tools over here were 0.02 error, so that's how we get these. By the way, if you didn't notice, I fused the deal. So yeah, that's pretty much it. This question was a big troll. This whole point, this point is, I mean, I believe this is an optional question, so I didn't really care too much if that was pointless. So whatever. But that whole top portion is basically junk. It is fluff that's meant to like, why the fuck do you even have that? Basically, I read it and realized it was pointless. You can read it if you want. I don't see the point in it. So you get the average of this, and over here there's 20 over here, so 1 divided by 20, which if you don't know, the average is adding everything up and dividing by the number of, how do I describe it? Well, just count them. There's 20 of the 20 of the individual numbers that they're given. So 1, 2, 3, 4, 5, whatever shenanigans, you get 20 over here. And if you add them all up and divide it by 20, you get the average because that's how averages work. You get all of them. Yeah, I don't know why I'm explaining that. It's kind of pointless to explain and thinking about it. We get SD, which is this, which is 3.9, and it was asked for, what was it again? The standard deviation, blah blah blah, is equal to square root of this. So over here we have Sn and we have n. If you square that, equals this, which is semi equal to each other. You could have also, if you wanted to, um, square rooted this. Let me get my calculator up. If I were to square root of this, why is it not pressing? 10.7. You will gotten 3.2, and I like red better. If I square root n equals 3.2, which is close to this number, which this is also a credible answer for B. If you wanted to do both ways, it doesn't really matter. Now, 4.14, where my statistics knowledge is coming into play, because this is where you use a chart. I know it says 0.27, so you could have done it more accurately, which means you could have gotten a better answer than me, which, sure, whatever, it doesn't really matter. I hope it doesn't matter. I don't think it matters on the test. Okay. Yeah, right. We use 4.6 knowledge, yeah. So B, how many measurements are in this range? What does that actually mean? It means that the t value is 1, which means it's basically 68%. Okay, which means 32% is outside of that 68%. Well, it's better to just show you. And I think I can use this over here because that's not being used well, in my opinion. Because I can clear this up and then use this over here instead of making a new frame, which I'm running out of frame because it's like 20. Really. So imagine a perfect bell curve, which a bell curve is same thing as Gauss's, I forgot, curve or something. It's basically if you drew something and had a middle. Okay, so it's basically what was it called? The chaos. If you drop a lot of marbles and into like a triangle pit, it makes this shape. Or you could think of it as, well, this portion has perfect symmetry to this portion. Well, it doesn't matter how you say it. So standard deviation is, if I say this is 69 and this is 7, the standard 71, the standard deviation is 2. But because the standard is 2, that's one standard deviation. Because if the standard deviation is 2, actually I can just better explain it if this actually shows up. Actually, I think I show by doing, right? Whatever. So let's say this is v, and this is 1. So that means it's 0 plus 1 this. Over here, if I do this, 0 minus 1 this. So imagine this being, what's the average again? What was the average? 10.7. Then the standard deviation is, what was again, 3.4? So this is plus 3.4, so it's like 14.1. And then obviously that's minus, and that's one standard deviation. If it's one standard deviation by Bell's curve, this is actually should be 68% inside. And we can determine by this table by seeing what what t value would correspond to what glass value should. So yeah, I accidentally clicked on something, which led to me another question. Well, 68%, right? So this portion is 68%. Um, that's basically the whole point of this question, which then two Bell's curve, but two. If you go down over here to 2, that's 95%, so it should be 95, where 5% is, by the way, it's asking for out, so you have to minus 68 to over here. So 100 minus 68 equals 32, which gives you, if you multiply it by 20 to 6.4, which is 6 out of 5, we count 5 out of there. We know it because 3.4 is deviation, so you can figure out the range of n is supposed to be, so 7 point, and then count over here like this one. No, that's not the right one. So like this one. That's one of them. You can, no, that's not right. Again, this one also counted. Yeah, that one counts. Like that one. You give them a mistake. Anyway, over here we have 20. But I mean outside of that range. So I was right the first time actually. What am I doing? So out of the range. So 7 would work. 6 would work because it's outside of that range over here of n. And then over here, 95 for 20v. No, 22 degree of. I think it's called degree of freedom, right? Whatever. So we get over here 0, 20. We just do 0.05 because that's the error version that I showed you, which is 1 out of 5, and we find 1 out of 5 inside of that error ditch. So we did that. Oh, this is more statistics. So if we do 71 minus 69, that's 2. That's 2 over here is standard ratio is 2. So you will notice that is this is 68. So 680 men are that height. 71 is more than that. So over here, this direction over here, which how you get it is kind of fun. I don't know if I showed it. There's two ways to actually do it. They show both ways. I don't know, whatever. So if we're thinking about this over here, we know that if I go over here 68, but I divide it by 2 because I want 34 and then add 50. That's one way to do it. The other way to do it, did I show it? No, not really. Okay, so it's 1 minus 68 divided by 2, right? So if I do 1, it means the whole thing, right? And then if I do minus 6, I'm minusing this portion. Then I divide by 2 because right now these two are left, but they're half of each other because they're symmetrical. So I get rid of one and leaving me with this last one over here. Um, right. Hope that makes sense. I'm basically saying this whole thing is 1, so I add that, and then I get rid of the 68 with this over here. There should be a point over here. And then I divide by 2, get rid, because there's 2 over here, I get rid of 1 to get the other side. Or you could do a 68 divided by half plus 50 and then minus 100, because that's how you get it, 84, 16. Either way, you get 16%. And this method is the same thing. Um, I think the last one is the most trickiest. Yes, because you're at 67, 68. So what you could do is, 65 is 2 dividation, which is 95%, and over here is 68. So you could divide both of them by two to get the area and subtract them each other, or just do it in this big equation, multiply by 1,000. There's many ways to do it. Not many. There's only like two ways probably to do it, and the all the variation is basically the rounding. You can round it to the second, round it to the first. Depending on how you round it, you get 136, 137, 138, 135. Now it just depends on how you round it, basically. So 36, 5.36 is about discrepancy, if I'm not correct. Yeah, discrepancy. What is uncertainty? So A is just getting the error, assuming all are independent and random. What is the discrepancy between these two? Which means what is the basically the difference between these two that you can see from one another, which you can. That's why you need absolute value. It is in chapter 5. Talks about it somewhere, if I'm not correct. I don't remember where it talks about it, but you have. Oh yeah, it does talk about it. It also talks about E, but I really don't understand why that question was given. The E question. Later on, we'll see what I'm talking about. But it's saying upsetly of major answers. Suppose we measure a quantity x in the standard form. I'm just reading off the textbook where the standard deviation is appropriate standard deviation. Suppose that based on some theory or what on someone else's measurements, expect the x, whatever, blah blah blah. It's just basically saying this equation t yeah. Basically saying this t equal that is what we need. If you want the full equation, it's basically t equal absolute x bex minus x exp, which expected divided by this. Which, yeah, that's a good uh, thing, but this also works for discrepancy because, well, you're saying that there's discrepancy between two measurements and you don't really know expected and non-best. So you're just basically assuming that one of them is best and one of them is expected, not really giving a shit about it. But in normality, in the normal what's again? I forget lab report. It would probably be expected value and best value, most likely not two students quantities and find the disparity between these two, because that's probably when you're doing research and you're actually searching for a new concept that you haven't thought of, the world hasn't thought of yet, which I don't think you're going to do until later on, at least not right now. You know. All right, so yeah, we can go to the next question. Basically, we're just doing that. We're just doing this equation up over here, and we're doing this equation up over here. So we're doing square root. I refuse to deal this to get this, and then you get this to over here. So what's happening is we're square rooting 1 square plus 1 square, which gives you this. I refuse to deal. Anyway, it's basically if you have an expected value, what would happen is this wouldn't happen. If you have the expected value, x best would have an error, but x expected would not have an error. So you could just use x expect as the standard deviation, and you should be fine, because x best is the average. Probably you will need the average deviation. What does that mean? Basically, square root of n divided by whatever's on top, the this, and then that would equal deviation, and just plug it back in. That's probably what's going to happen for your labs, because that's what happened to me, basically. I never got a question that had two things that we find this. That's probably more research focus idea, because that makes more sense in research topics than doing it. Yeah, you know what I mean. So if it's think about it, if you have a curve and it says like 5% less, if you get something that inside of this range and there's outside like 16%, that's fine. But if you get less than 5%, there's some kind of problem and it's significant enough that you actually need to rethink about this because there's some amount of error here that has that makes it significant, and there's probably something you did wrong or some kind of device error that could have caused this much error, which then you might need to look at what the reasoning. But yeah, that's basically it. So uh, I think we're good on here. Oh, the next part you don't need. It's basically this shenanigans, and this is just derivation. These are two separate questions. This is part A, part B. Prove that the function is normal. Let's find this. Basically, this equals t. Um, basically, this is not part of this class. Basically, this is just extra questions that you don't need. Basically, I did it for you can do it for fun, but it basically tells you about these two shenanigans and how Taylor series works. This is way more important. This is way more important, but it's not going to be on the final probably because it's optional questions and then it's 1 star, which means that he doesn't think it's gonna because it's usually 1 to 2 stars in between that we have it in the midterm or test, and the professor really didn't talk about this much. And sure, if it's derivation, we might get it. One derivation, but I haven't seen any slides that demonstrate that we'll use this. Although it's fun to look at least.